Today we'll be, my name is Renu Raman Sahu, and today we'll be discussing some of the question and answers of assignment. Uh, week 4 of 2023 and the fifth assignment of previous year. So let's start with the questions. So uh, the first question is the energy dispersion of electrons in one-dimensional lattice is given with some lattice parameter. So the dispersion relation is given. Okay, so dispersion relation is the relation between E as a function of, where E is written as a function of K, or the uh, wave number. So it is given as E naught minus W by 2 cos Ka. Okay, where all other things are constant, W naught is a constant, uh, A is a constant, this is the lattice constant, and A naught is also a constant. So we have to find what is the effective mass at the bottom of the band. So we have to find what is the bottom of the band and what is the effective mass there. So let us first draw this E versus K relation. So if you draw this, how it will look like? So we plot E on the y-axis and here K. So it will be something like minus cos Ka. So it will have some this form. It will look something like this. And the bottom of the band, yeah. So we're discussing about the how to find the effective mass of the electron at the bottom of the band where the energy dispersion is already given. So the energy dispersion, it will look like inverted cos function like this, and the bottom of the band is this point where there is the minimum, and this will occur when k is equal to 0. So k equal to 0 is the bottom of the band, bottom of the band, or the place where dE by dk is equal to 0 and d2e by dk square is positive. Okay, this is how, like, here it is very intuitive to find what is the bottom of the band, but if the question is somewhat complicated and you don't have any idea of the dispersion relation, then you have to find the bottom of the band by using these two equations. Okay, so now we have to find the effective mass of the electron. So effective mass of the electron, the way to find is, let me first give you the definition of the effective mass. So energy, it will be given by, so we know that this is the formula of the uh, uh, 2m. This is the general dispersion relation of a particle. So for effective mass, what we do, uh, like if it is in some other system, here this m need not be the mass of the electron, so it will be the effective mass. And to find this, what we do, suppose let's say we do the derivative once, do but k, then what we get is h bar square k over m effective, and if we do the derivative again, k square is equal to h bar square over m effective. So m effective is nothing but it is h bar square over 2e by dk square. Okay, so we have to find this quantity. So the double derivative of the energy at bottom of the band. Bottom of the band means k is equal to 0. So let us do that. So let us do, so we have this expression. So we do the derivative once, dE by dk, that will be minus w by 2. So it will be minus a cos, cos derivative of cos is sine k. Again we do the derivative again, by dk square is equal to minus w by 2a square cos ka. Now we want to put k is equal to 0. So k is equal to 0. So what we have is minus w a square by 2. Oh, so this minus minus, it becomes plus. So it is this. So what we have here is, we can now put this here, and then what we have is, this will be equal to h bar square over w a square by 2, which is your answer. So this is your answer. So the point to remember is, you should know how to you have to remember just this is your working formula. If you know this, you can solve this kind of problems. Okay, so now the second question, the EK dispersion relation of a particle in 2 dimensions. So here one thing important is to note that the dimensionality. The dimensionality is 2 dimensions, and the dispersion relation. Dispersion relation means energy as a function of K. So this has to be there. So this can be any relation. It is given a linear dispersion relationship, but it can be some other form. For example, any other non-relativistic particle, it will be h bar square k square by 2m, or some it can be a relativistic particle. For it, there will be another relationship for k. So this you have to keep in mind. It can be any function of k, and c is a constant. So if the density of states is dE is proportional to e to the power p. So let us see how we can get this density of states. So to find the density of states, what we do is, so this is the general procedure how we go. So the number of states will be given by L over 2 pi. So you write L over 2 pi, and we want 2 dimension. So we so here it goes the dimensionality. Okay, and integral minus infinity to infinity dkx minus infinity to infinity dky. Okay, so this is how you find the. So if it were some other dimension, let's say dimension d, or dimension, yeah, let's say dimension d, then here it would have been L by 2 pi to the power d, and this one dk1 integral minus infinity to infinity, then minus infinity to infinity to dk2, so on up to dkd. Okay, so that is how you have to find for a general dimension. But now let us do it for d equal to 2, which is 2 dimension. Okay, so now what we have to do, and we have to multiply one more 2 for spin. Okay, uh, so usually we find the number of states per unit volume, or like in, since it is 2 dimension, we will find number of states per unit area. So L square, we'll write it as A, and we divide L square on both sides. So what we'll have, number of states per unit area will be 2 1 by 2 pi whole square. And so this is, now you see, this is in a Cartesian coordinate. So we can convert it into a cylindrical coordinate, and in cylindrical coordinate, so what this means is, so it is taking, so dkx dky and integrating over all the entire space. So this is dkx dky. So instead of that, what we can do is, we can just simply think of it as we'll think of it as a very small circular strip at a distance k of thickness dk. Okay, so it will be 2 pi k, which is, so it is kx. So the radius, you can think of it as k. Okay, so 2 pi k is the width of is the circumference of this, and dk is the thickness of this strip, thickness dk. Okay, 0 to infinity. Now what we have to do, you have to put in the, now we have this e as a function of k, right? So we will find what is dE. So we have to use this thing, dk. Okay, now E, we know what is, E is ck. So So here we use the fact that E is a function of k. So this will be, so E of k, this is C k, and this thing will be C d k, or k is equal to E by C and dk is equal to dE by C. So you just put that, so 2 by 2 pi whole square, again, or 2 pi integral 0 to infinity, and this is E by C square dE. Okay, so basically what how the density of states is defined as, so density of states will be defined like this, from 0 to infinity. So any density of state, it will be number of states per unit area is uh, number of states per unit area, or if it is 3D, then number of states per unit volume. It will be integral 0 to infinity dE, uh, dE times dE. Okay, so here on comparing, so this thing is equal to this. So here what we get here is dE is equal to, this is 4 pi over 2 pi square whole square into C square to E. So here you see that this is directly proportional to E and the power is 1. So it is directly proportional to E to the power P, and P has to be equal to 1. So this is how you have to do. And now you can, so you can similarly do for any arbitrary dimension. So D can be in some other questions, you may be asked like 2, 3, for anything you can do. Okay, so now let us go to the next question. So I hope this is clear, how to solve this type of problems. Okay. If there is any doubt at any point of time, you can stop me and ask. So now let us go to the next question. Which is the correct statement about the Brillouin zone of a square lattice with lattice constant A? So let us see first how the Brillouin zone of a square lattice with lattice constant A will look like. So in the real space, we have this. The lattice constant is, so the lattice will look something like this. It is a square lattice, and this thing will, the lattice spacing is A on both x direction and y direction. So the corresponding, in the K space, how it will look like, in the K space it will look like this. So the Brillouin zone will be also a K vector, it will also be a square lattice, but the spacing would be now 2 pi by A. Okay, how do you know this? It is 2 pi by A, K space. So how do you know that it is 2 pi by A? You can use the simple formula for the Brillouin zone to finding the, so A1 you can write A x cap, and A2 you can write, so in real space, okay, A2 equal to A y cap, and A3 you just write some z cap. So these two are real space, and so this we are taking for a calculation is, so in reciprocals vector, how do you find it? You find it by b1 is equal to 2 pi over a1. So denominator has to be a some, it cannot be a vector. So what we do is we multiply a2 cross a3, and here this will give you a vector, and here we will do a2 cross a3. So this is a vector quantity, and it will do the dot product with this vector, and it will give you a scalar. So this will give you 2. So if you just put all these values, it will be 2 pi by a x cap. Similarly, you can find b2 is equal to 2 pi over a2 dot, here a1 cross a3 divided a1 cross a3. Okay, So this will give you 2 pi by a y cap. Okay, so this is how your preload zone will look like. The K space will look like. And how you calculate the preload zone? It is like this. So the first preload zone, you just draw the dots and take the just a second. Yeah. So the way we find the Brillouin zone is, the first Brillouin zone is, you first take this and draw. You join the first cell. You join the. Suppose if you want to find around this, the first Brillouin zone along this, then you draw the lines to your nearest neighbors, and then maybe the next nearest neighbors as well. Then you draw the lines which are bisecting this. So this line will be bisected by this line will be bisected by this, and this is your first Brillouin zone. Then your second Brillouin zone will come when you join the bisectors of the next nearest neighbor. So for this line the perpendicular bisector is this, for this line the perpendicular bisector is this, and similarly here and here. You see, the first Brillouin zone is so I'll use other ink. So this is your first Brillouin zone, the one which is which I'm shading in green. So this is your first Brillouin zone. If you note this, and the second Brillouin zone is what? The second one is let me use some other color. This is your second Brillouin zone. This, and this. Now you see, you see this, just an observation, that if you have, you just draw like this. See, this area is same as this area, same area. Similarly, this is same as this, and this is same as this, and this is same as this. So the area of first Brillouin zone is equal to the area of second Brillouin zone. Okay, so that is why these two are same, and this is true for all the Brillouin zones. So this will be equal to the third Brillouin zone, area of third Brillouin zone and fourth Brillouin zone. So you can verify by doing the similar construction of Wigner seed cells. So this is how. So all the Brillouin zones, their area will be the same. Okay, and here let us see the other options as well. The first Brillouin zone is a square of side pi by 2a, but like from this calculation we see that it will be of side 2 pi by a. So this is wrong. The k points are not equidistant in kx as well as ky, but here we see that the k points in x direction is 2 pi by a separated, and here also it is 2 pi by a separated. So they are equidistant. Okay, so this statement is wrong, and the area of second Brillouin zone is twice as that of first. So this is wrong because we proved here that it is the same. Okay, so I hope this concept is clear now. We'll go to the next question. Okay, so given, so delta ij is also called Kronecker delta function. This is also called Kronecker delta. Okay, and this is how it is defined. It is 1 if I is equal to j, if these two indices are same, and 0 otherwise. And we have to find this quantity where j is equal to 1, 2, 3 and 4. So it is just a simple, we have to just expand it. So j delta j j. Okay, and j, it varies from 1 to 4. So 1 to 4. So it is nothing now. We simply have to expand this. So it is delta 1 1 plus delta 2 2 plus delta 3 3 plus delta 4 4. So now we will use the definition. Here we see that delta 1 1. So 1 I, the value of I is 1 and j is also 1 and both are equal. So delta I will be 1. Similarly, delta 2 2 will also be 1 and delta 3 3 will also be 1 and 4 4 will also be 1. So this is 4. So now let us go to the next question. Consider a band with anisotropic dispersion relation. So we have been given a anisotropic. Why anisotropic? Because if you see kx, if we see in the k space, kx, ky and kz. So for a given energy, means so imagine a surface with constant energy. Okay, if you draw that in this kx, ky, kz space, it will be something like an ellipse. Ellipse means the distance at which kx will this ellipsoid will intersect kx, ky. So at this point, and this point, this need not be same. Okay, and this need not be same. So that happens for cases where the material is anisotropic. Anisotropy means in all in different directions there will be no symmetry. So along a particular direction there will be some different spacing of the lattice spacing, and in other direction there will be some different lattice spacing. In those type of materials it will happen. So now so it has given the fact that what is the volume of an ellipsoid. So volume of an ellipsoid, it is given 4 pi by 3 ABC. We have to find what is the density of states. Okay, so if you remember the way we derived for the isotropic case, in which mx, my, mz was the same. So mx, my, mz was same, then we could have taken this mx, my, mz common and taken it out. So it will be h bar square by 2m into k square. But now it is the different case. So in that case, the density of states, how we used to find? We used to find, so density of state is number of states G of E is equal to number of states per unit volume per unit energy range, or it is the number of states per unit volume between energies E to E plus dE. So if we take two different energy cells, okay, so the energy of this is E and energy of this is E plus dE. Then what are the number of states which are available in this particular cell? That will give me the number of states. So this number of k space, and we have to multiply it by 2 for the spin, because there would be 2 spin up and down. So we have to find what is the number of these dots, or this what is the number of this k points. So we know that every k point, so every state along it will give a contribution of every state will have a contribution of 2 pi over L by 2 pi. So let us say that the volume. Okay. So what we have to do so if we want to find what how much is what is the k space volume of one particular state, similarly ny equal to ly ky over 2 pi and nz is equal to lz 2 pi. This thing is clear, right? That this is how the states are counted. Okay. And we have to what we want to do is what we want to find the k space volume of volume in k space for one k state. So it will so what we want is this delta n x, delta n y, delta n z, this would be 1. Okay. And this will be 1 if we have, so it is lx delta k x by 2 pi, ly delta k y by 2 pi, and lz delta kz by 2 pi. So delta kx, delta ky, delta kz. So this means this is the k space volume for one k state. So it will be 2 pi whole cube over lx, ly, lz, or 2 pi whole cube divided by the volume of the material. Okay. So this is the volume in k space for one k state. Okay. Now how can we find what is the number of dots or the number of k states in this cell? So we have to find what is the volume of this particular cell, ellipsoidal cell, divided by the volume of one k state. That will give me the number of k state in this particular cell. So let us just find that. So this is E, and this is another cell at E plus DE, and we want to find what is the number of k states in it. What is the number of k states in it? We already have seen that delta kx, delta ky, delta kz is equal to 2 pi whole cube over volume. This is for one state. K space volume of one state. Okay. Now what we want to find is the volume between these two. So what we can do is so we have to use this information now. So we have been told that so this is the equation of an ellipsoid. So here, okay, this is kx, ky, and kz. So we are given this particular volume. So kx by a whole square plus y by b whole square plus z by c whole square is equal to 1. This is the if this is the ellipsoid, then the volume will be given by 4 pi by 3 a b c. So for this ellipsoid, what would be this A, B and C, that we have to find out, and that we can get from the dispersion relation. So the dispersion relation is given by, so this is our dispersion relation, energy, or the energy is given by h bar square by 2 kx square by mx plus ky square by my plus kz square by mz. Okay, so this we want to write it as this particular form, so we divide everything by energy. So it will be kx square by 2mx energy by h bar square, and so we want to write as that form. So what we will do is whole square. Similarly, ky by square root under 2my h bar square whole square plus kz square 2mz h bar square whole square. Okay, so the volume of k space volume of the ellipsoid, okay, of the ellipsoid with maximum energy epsilon, it will be given by, of the ellipsoid is given 4 pi by 3 ABC. Now our ABC is the denominator of x, y and z. Here it will be the denominator of kx, ky and kz. So it would be 2 2mx by h bar square 1 by 2 2my h bar square 1 by 2 2mz by h bar square to the power 1 by 2. This is how it will be. But now what we have to do, we have to find, so basically the strategy would be, so at E, so this is ellipsoid at E, and what we want to find is what is the number of states between these two. So we want to find k space volume. So what I will write it as the volume in k space at energy E. Okay, of, I'll write denominator k because it is in the k space, or we can write this omega is where omega is the k space volume between E and E plus dE. So this will be given by just d omega by dE. Okay, it's dE. So this will be your k space volume between these two. So what we will have is, so this is, so we'll put all the constants together, 2 pi 4 pi by 3 so 4 pi by 3 and it is 2 root 2 over h bar cube, and it is mx my mz 1 by 2 3 by 2, and we have to do the derivative with respect to energy. So this will give me 4 pi by 3 2 root 2 by said 1 by 2 3 by 2. Okay, so this is the k space volume between k space volume between E and E plus dE. Okay, so this is d omega by dE into dE. Now what we want to do is we want to find the number of these points. So we have to divide the number of k states will be this quantity divided by the k space volume of one state. Okay, so now all we need is we have to divide this quantity by this quantity. So what we have is the number of k states between E and E plus dE is equal to d omega by dE over. So this is the k state for k space volume of one state, one k state, and this is the k space volume of ellipsoidal cell. Okay, so we just have to evaluate this quantity. So what we have is from previous slide 4 pi by 3 4 pi by 3 2 root 2. So that was the numerator, and the denominator would be 2 pi whole cube over v. Okay, so this is the number of k states. Now the number of states between E and E plus dE. So here we have to multiply another factor due to spin. Okay, so this was the number of k state. For each k state you have to we have two spin states, so that is why you have to multiply by this 2. Okay, so now number of states per unit volume between E and E plus dE. So since it is per unit volume, we have to divide by this volume now. So it will be 2 4 pi by 3 2 root 2 by h bar cube, and this is 3 by 2 mx my mz 1 by 2 dE over 2 pi whole cube. Okay, so we have to find, so the question was asking about what is the density of states. So the density of state is defined by like this: number of states per unit volume per unit energy range. So it is so what we have to do is we have to now divide by the energy range. So what is the energy range? Energy range is just dE. Okay, so what we have to do, the number of states per unit volume per unit energy range. So it is just, so we just have to divide by dE. So if you just take that factor out, so you will be left with this 4 pi by 3 2 root 2 over h bar cube 3 by 2 mx my mz this to the power 1 by 2. Now it is just a matter of simplification. So this is nothing but your definition of density of states. Okay, or and this quantity is nothing but GED. This is the number of states per unit volume between energy E plus E and E plus dE is given by this quantity, and this is your density of states. So you just have the density of expression, density of states expression like this. So let us simplify this, and you'll have your answer. This 3 cancels 3, 2 cancels 2, and so there is. So on simplification, you will get this answer. You will get this particular answer. So I will just write it down. So pi square, because pi will cancel 1 pi in this cube, and this will. So here it is 8. It will cancel these two. These two will come into this bracket because there is a square root. So 2 mx my mz 1 by 2, and there would be this h bar cube. So 1 h bar I can take into this, so it will h bar square, because there is this 1 by 2 factor here. So this is how. So this is your required answer. Okay. So this is how you do the density of states calculation for this ellipsoidal problem. Okay. I hope this it was clear. Now let us go to the next question. Here what you have been given is that consider a metal which obeys the Sommerfeld model. What is Sommerfeld model? Just to recall you, Sommerfeld model takes into account the fact that electrons are fermions and they obey Pauli exclusion principle, and that is why they obey this Fermi-Dirac statistics. Okay, and here this is at EF. So this is your Sommerfeld model. And EF is the Fermi energy of the metal at T equal to 0 Kelvin. So at T equal to 0, so the occupation state will be like this. Okay, there will be no smearing out, it will be just a step function. And RH is the Hall coefficient. The Hall coefficient, if this is the Hall coefficient, we have to find a relationship between the Hall coefficient and the Fermi energy. So if you remember, the Hall coefficient is given by 1 over NE, where N is the density of electrons, or the number density of electrons, and E is the electronic charge. So at T equal to 0, the density of electrons, so at T equal to 0, the Fermi energy, it is given by h bar square by 2m 3 pi square n to the power 2 by 3. So this you can easily derive by using the fact that the number density of electrons, it will be given by 0 to infinity, and the density of states and the occupation probability dE. Now if you use the fact that t equal to 0, by using this fact this integral will become 0 to EF, because beyond it everything is 0. So GE DE. So if you calculate this, you will get your desired result. So basically the point is EF, or the Fermi energy, is directly proportional to n to the power 2 by 3, or conversely n is directly proportional to EF to the power 3 by 2. Now we know that the Hall coefficient, it is the Hall coefficient is 1 over NE, which is inversely proportional to n, and this is n is directly proportional to e to the power 3 by 2, so it is e to the power minus 3 by 2. So this is your desired answer. I hope this is clear. Now let us go to the next question. Here we are given a general form of UM is the general solution, the form of the general solution is given for a dispersion relation. Okay, so this tells you that it is a quadratic, so this dispersion relation, it tells you that the lattice is uniformly spaced, and so lattice is something like this. Okay, and UM is given by a e to the power I m theta plus b e to the power minus I m theta. So under periodic boundary condition, so what is this m? M is some index of this atomic number. Let's say it starts from 0, 1, 2, 3, 4, so on, let's say n. Then again it will start from, so if we associate that periodicity is n, so we have to associate these two are equivalent. So U0 for periodic boundary condition, U0 should be equal to UN. U0 should be equal to UN. So what we have to do is, let us just try to do U0 equal to UN and see what we get from the periodic boundary condition. So this is your periodic boundary condition. So U0 is nothing but A plus B, because m equal to 0 and e to the power 0 is 1, and UN is equal to A e to the power I n theta plus b e to the power minus I n theta. Now if you want to do U0 is equal to UN, then what we have to do? A plus B is equal to A e to the power I n theta plus b e to the power minus I n theta. So just for the sake of some simplification, let us do this. Let x equal to e to the power I n theta. So 1 by x will be e to the power minus I n theta. So we will just use that a x plus b by x equal to a plus b. So what we have is, so a plus b, so we multiply everything by x, so ax square plus b. So ax square minus a plus bx plus b is equal to 0. Okay, so this we can write it as ax square minus ax plus minus bx plus b is equal to 0. Now this will be equal to ax x minus 1 plus minus b and x minus 1 is equal to 0. So this will be ax minus b and x minus 1 is equal to 0. So here if x is equal to 1, then you have x equal to 1. So this will give x equal to 1. Okay, so x is what? E to the power I n theta is equal to 1, and 1 you can write it as e to the power I 2 pi k, where k is in some integer. K is some integer. Okay, so from here what you can write, from this condition, I n theta is equal to I 2 pi k, and theta is equal to 2 pi k by n. Or 2k pi by n. So this is what you will get. I hope this question is clear. Now we'll go to the next question. Okay. So a few questions before we saw how to get the density of states for a 2 electron gas. So what this question is asking, what is the Fermi energy of the system in electron volt? So we have to find the Fermi energy of the system. So let us do that. We'll use a similar procedure. So let us first find what is the number of electrons. So the number of electrons, or the number of let us find the number of states first, and then we'll get the number of electrons. So number of states in 2-dimensional states is equal to L by 2 pi whole cube whole square. Now square because it is a 2-dimensional. This 2 is for spin, and integral minus infinity to infinity dkx minus infinity to infinity dky. This is the number of states. Okay, and now what we want to find, number of states per unit. So here the density means number of electrons per unit area. Per unit area. Okay, so the number of states per unit area, where A is equal to L square, it will be given by 2 over 2 pi whole square, and this dkx dky I can convert it into the cylindrical coordinate, 2 pi k dk 0 to infinity. Now what I will have is, so this is the number of states. So number of electron per unit area, or the number density of electrons, or n, this will be 2 over 2 pi square, 2 pi square, 2 pi k dk. Now it will be 0 to kf. Okay, at so Fermi, if you want to find Fermi energy, you have to find at t equal to 0. At t equal to 0, you remember that the occupation probability, it is just a step function up to EF. Okay, and EF is nothing but h bar square kf square by 2m. Okay, so if we just do this, what we get is 2 over 2 pi whole square, again 2 pi, and it is kf square by 2. So this is what we will get. So kf, so this 2 will cancel this 2, square by 2 pi. So kf square will be 2 pi n. Okay, we know that the Fermi energy is equal to h bar square by 2m into kf square. So kf square you just substitute h bar square by 2m into 2 pi n. So you have been given n, and you have been given h bar you have been given, and value of m also you know. So this will give you energy in joules. But if you want to find in electron volt, what you have to do? So EF is equal to h bar square by 2m into 2 pi n into electron volt by electron. So electron and volt is in SI unit. So if you multiply it with the electron, you have to divide it by the electron. So this, where E is nothing but 1.602 into 10 to the power minus 19 electron volt. So if you calculate this quantity, then you will, whatever the number you will get, that will be having the unit of electron volt. So if you just put all these values, what you will get is around 2.34 electron volt. So all these values are given. You just have to put and get the answer. This is clear, right? Like, I hope it is clear. Okay. So we have derived what is the number, or what is the Fermi energy of the system, of the two-dimensional system. So now let us go to the next question. Which of the carbon allotropes can be formed by graphene? Graphene, if you remember, graphene is just a two-dimensional material in which is this hexagonal shape. Okay. So these are the planar sheets of graphene. So at each of this there would be carbon atoms. So carbon nanotube would, so if so this will be actually a very long, it is a very planar material. Okay, so it will be kind of a plane. Okay, and if you just roll this, you will get the carbon nanotube. If it is formed into a sphere, like there will be a spherical thing, and there will be, it is like a very big football kind of thing. So it will be a fullerene. And graphite is nothing but the planes of this hexagonal structure, which are stacked on top of each other. So graphene is just one layer. Graphite is a stacking of all this. Okay, so this is one layer, and there would be some van der Waals force kind of thing, and it will hold to the next layers. So this is graphite, graphene, buckyball, and this is, if you just roll this, you will get a carbon nanotube. So all of this can be formed by graphene. So now the next question. So for graphene, the energy spectrum has been given. So this is the formula, and we are asked what is the value of the energy E at a given point. So this point kx is equal to 0 and ky is equal to 4 pi over 3 root 3a. Okay, and we have been given epsilon naught is equal to 0 and t is equal to minus 1. So this thing is 0, t is minus 1, kx is 0, so cos 0 is 1. So the value of this will become 1 because cos 0 is 1, and we just have to find ky root 3 by 2 a naught. So the ky root 3 by 2 a naught, it will be nothing but ky, we have to put it from here. So 4 pi over 3 root 3 a root 3 by 2a. It is nothing but root 3 cancels root 3, a will cancel a, 2 will cancel, it is 2 pi by 3. And we know that cos ky root 3 by 2a will be cos 2 pi by 3. Cos 2 pi by 3 is minus 1 by 2. Okay, now we have everything, so this cos of this thing is minus 1 by 2. Okay, and cos of kx 3 by 2a, kx is equal to 0, so cos 0 is equal to 1. So we just have to find what is the value of e. We have to just substitute. So 0 plus minus t equal to minus 1 and 1 plus 4, and so 4 into minus 1 by 2 into 1, which is minus 1 by 2, and plus 4 into minus 1 by 2 whole square. So what we have is 0 plus minus 1 minus 2 plus 1, which is nothing but 0. So the value of energy at this particular point is 0. So this is your assignment 4. Now let us go to the previous year assignment 5. So the first question, it is asking what is the value of the in the Hall measurements, sodium conductor is given and a transverse field. This is, let's say this is that sodium conductor. And a transverse field was found to be equal to some transverse field has been given. Transverse field means, so there would some field would be there along this direction. Okay, some transverse field is there, and the current density is given. Current density means the electrons are flowing. So current density, it is given by current over the cross section area. The cross section area is this area. Okay, current by A, it is 200 ampere per centimeter square, and the magnetic field induction B, so let us say that magnetic field induction is equal to 1 Tesla, and the concentration of the electrons is, so concentration N is eta times 10 to the power 22 per centimeter cube, and we have to find what is eta. So the way we do is this. So let us imagine that there would be an electron. That electron is, so since current is going in this direction, that electron would have been traveling like this, and because of the presence of magnetic field, it will experience a force. So F magnetic field. Yeah, so this will experience so this will experience a force due to the magnetic field. Force due to the magnetic field in this direction, F magnetic. So electrons will be accumulated here, minus, and here there will be some plus charges generated here. So basically your field will be generated like this. Your field will be generated like this, and because the field or the Hall field will be generated like this, the force due to the Hall field will it is opposite to the direction of the current, opposite to the direction of the field. The force is opposite to the field because electron is negatively charged. So it is E V B, force due to the magnetic field. So it is E V cross B, and it is E H, or the Hall field. Hall field is this 5 microvolt per centimeter, and from derivative theory we know that the current density J is equal to NEV, or V equal to J over NE. Okay, so what we have is J by NE. So this E cancels, into V is equal to E. Yes. So this will give me N is equal to J B by E into EH. Okay. Now all you have to do is put this values and get what is the current density. Okay, so let us do that. So but we have to keep in mind about the units. The units are in, so we have to put either put during the calculation it is good to put all the units should be in SI, and then you have to report the answer in centimeter cube. So you convert all the units to SI. Take care of all units. Okay. So let us do that. So J is given by, so N is equal to 200 ampere per cm square. B is 1 Tesla. So this is already in SI unit. Ampere is in SI unit, but centimeter is not SI unit. So electron is 1.6 into 10 to the power minus 19 coulomb. This is also in SI unit. EH is 5 microvolt per centimeter. So now you see that microvolt is not SI unit and centimeter is not SI unit. So you have to take care into take this into consideration. So we have to convert everything into meter. So if we convert into meter, so it will be 200 and it will be 10 to the power minus 6. So it will be 10 to the power 6 yeah, so 10 to the power 6 ampere per meter square. So now since it is in SI unit, so we don't, so it is fine, and it is 1.6 into 5 into 10 to the power minus 19. Microvolt is 10 to the power minus 6 and centimeter is 10 to the power minus 2, so it will come plus 2. Okay, if you evaluate all this, you will get so what you will get is in meter cube. So whatever you will get is number of this many number of electrons per meter cube. Okay, if you want in centimeter cube, again you have to convert this back into the centimeter cube. So so you just have to remember this 1 meter cube is equal to 10 to the power 6 centimeter cube. Okay, so what you have to do is so this is so if you use this conversion unit, you will get the desired result to be 2.5 into 10 to the power 22 per centimeter cube. Yeah, just take care of all the units, you will get this answer. Now we go to the next question. So what it has been given is the Hamiltonian of the graphene is given and f of k is given. Let us find the k and k points of Brillouin zone of graphene. And how do we find that? In order to identify the Dirac points, we take k f of k equal to 0, or we have to take the complex conjugate to 0. So solve ahead and find the correct option for k and k prime. So okay, it is everything has been given. We just have to solve and find the results. So what do we have to find? We have to find f of k is equal to 0. So let us do that. F of k is equal to 0. K is k vector. So it is minus t a to the power I k x a plus 2 e to the power minus I k x a by 2 cos root 3 by 2 k y a is equal to 0. Okay, so so it will be 0 when this quantity is 0. We can cancel this minus t, that is usually some non-zero number. So what we have to find is e to the power I kxa plus 2 e to the power minus I kxa by 2 cos root 3 by 2 kya is equal to 0. Now we know that this e to the power I theta, this is called Euler formula, cos theta plus I sin theta. Okay, so we will just use that formula. So it will be cos kxa plus I sin kxa. Then we have to expand this also. So it will be 2 cos kxa by 2 cos root 3 by 2 kya plus times 2 sin. Now minus, so one point to remember is that cos minus theta equal to cos theta, so it is actually cos minus kxa by 2. So minus kxa by 2 cos root 3 by 2 kya. This has to be equal to 0. So the real part has to be 0 and the imaginary part has to be 0. So the real part, what are the real part? These two terms are the real part. So what we have is cos kxa plus 2 cos kxa by 2 cos root 3 by 2 kya is equal to 0. This and the and so this is the real part, and the imaginary part has to be 0 as well. So it will be sin kxa plus, so sin, so this is 2 sin minus kxa by 2 cos root 3 by 2 kya is equal to 0. Okay, so now what we can do is, so this is imaginary part. So we want this to be 0 simultaneously. So what we can do is, so let us first expand this one. 2 sin kxa by 2 cos kxa by 2 minus 2 sin kxa by 2 cos root 3 by 2 kya is equal to 0. Okay, so if you simplify this, what you get is 2 sin kxa by 2 and in cos kxa by 2 minus cos root 3 by 2 kya. This has to be equal to 0. So what we have is, from here, sin kxa by 2 is equal to 0, which means kx is equal to 0. Okay, this okay, so kx equal to 0, that is what we got now. Now we have to use this. So this we did for the imaginary part. Now we have to ensure that the real part is 0 as well. So since kx is equal to 0, what we will do, so kx is equal to 0, so cos 0 is 1, so cos 0 is 1 plus 2, so again this is also 0, so this is 1, and this will be cos root 3 by 2 k by a. This has to be equal to 0. So what we get is cos root 3 by 2 k y a should be minus 1 by 2. Okay. So here we already see that all the options have kx equal to 0. Okay. We have to find what is the value for this. So we'll get it from here. So what we have is cos root 3 by 2 k by a is equal to minus 1 by 2, and minus 1 by 2 it is cos 2 pi by 3, and cos, since it is an even function, plus or minus it doesn't matter. Okay, so basically root 3 by 2 k by a should be equal to plus minus 2 pi by 3. So from here we can get ky is equal to plus minus 2 pi by 3, and so 2 will come here and root 3a is coming here. So what we have is plus minus 4 pi over 3 root 3a, which is your option, the second option. So that is how you have to solve this particular problem. Now let us go to the next question, and so kx was 0. So on previous page. Okay, now let us look at this question. So for a two-dimensional unit square lattice, so two-dimensional unit square lattice, A corresponds to half filled band. So what value of A? So what is the value of A that corresponds to half filled band? And we have to take epsilon naught equal to 0 and t equal to minus 1. So what this means is, what is epsilon naught and t? So this is so for two-dimensional unit square lattice, we have to first look at what is the energy dispersion relation. So if you do the tight binding model, in which you will have some hopping integral, for example the on-site integral is, let's say, epsilon naught, and hopping integral is minus t, then what you have is the energy dispersion relation. You can prove that A of k is equal to epsilon naught minus 2t cos kxa plus cos kya. So this is what you will get if you solve for the tight binding, the energy dispersion in the framework of the tight binding model. Okay, so now let us look at, so it has been given that epsilon naught is 0. So epsilon naught equal to 0 and t is equal to minus 1. Okay, so if we just put that, what we get is epsilon of k, or this is the energy, epsilon means energy here. So 2 minus 2 and minus 1. Oh, sorry, 4. So what we will get here is 2 cos kxa plus cos ky a. Okay. Now, how does this function look like? If you uh, if you try to plot in some 2D in a, as a 2D plot, so for this is, let's say, kx and ky, and here you put e of kx and ky. So this will look like something like this. Okay. So this is your kx ky, and energy is along this z direction. So it will have a surface, see that this will have a symmetry at origin, because cos kx is symmetric about origin, cos ky is also symmetric around origin. So along ky it will look like this. Along ky, if you see, it will have, it is a cos function, and along kx also it will be, so along kx also it will be similar, but it will be, so imagine that this cos has to be in this direction. So this is energy, and so it is in this direction. So this will intersect here. So basically it is a kind of a so it will be like this in this direction, and it is varying like this in y direction. So basically the way you have to think of it is, I'll just try to draw how it will look like. So it will be kind of a ball, which is, you're able to imagine this, right? Like it is a kind of a ball, uh, which is like, it has a surface like this. It has a minima here and a maxima here. So or it will look something like this in uh, so I hope you are able to imagine what it will look like. Okay, so there is a minima at the center. Uh, okay, so the minima, you can just find out what would be the minima. Minima when this will be, so when this will be 1 and this will be 1, so it will be 2. So minima will be -4. Okay, and the maxima will be when it is -1, when it is -1, it will be +4. Okay, and there will be a symmetry. So if the topmost part is +4 and the minimal part is -4, the half filled band, it will so around 0 there will be a symmetry. Around 0 there will be a symmetry. So half filled band will be just the middle of 4 and -4, which is nothing but, so the half filled band in which the electrons will be filled up to the half of this thing, which is the middle of this, and that will be corresponding to E equal to 0, because it is, because of symmetry we can say that it will be the mid of E max and E min. So that is why E is equal to E min mid. So by symmetry of this function. Now let us go to the next question. So I hope this is clear. Uh, so now let us look. What is the question is asking about the velocity of the electron at the boundary of first Brillouin zone of a crystal. Okay, so the velocity is given usually by. So let us say, suppose if you have forgotten the expression for the velocity, how do you find it? So this is just a trick to remember. So energy, we know that it is p square by 2m and p is equal to h bar k. Okay, so if you do the derivative once, dE by dP, what you get is p by m. So p is mv, the mass times velocity, by m, and so this is nothing but your velocity. Okay, so velocity is given by this. So velocity is given by dE and p is h bar k, so dE by dk. So this is in 1D, and in general if you want to calculate the 3-dimensional one, so what you have to do, it is 1 by h cross, and you have to take the gradient of energy. Okay, so or basically it is Vx equal to 1 by h cross, the partial derivative with respect to kx of energy. Vy is equal to 1 by h bar to partial derivative with respect to kye, and similarly for Vz. Okay, so this is how it is. So the at the boundary of first Brillouin zone of a crystal, so how does it look like? Let us look at one dimension first. In one dimension, what it will be? So energy as a function of k, it looks something like this. Therefore, this is pi by a, and this is minus pi by a. The first Brillouin zone. We see here that so if you take care into the tight bending approximation, then so it will go like this. Okay, this is the boundary of the first Brillouin zone, then the second Brillouin zone start. Here you see the derivative dE by dk is equal to 0, and from this we know that the velocity is dE by h bar dk. Since dE by dk equal to 0, so it is 0, the velocity will be 0. So this is for one dimension. For any other case also, at the boundary, so by 2k it becomes 0, even in any other dimension also. So that is the answer of this question. So we go to the next question now. So what we are asked is, consider the following statement and we have to choose which of these statements are correct. So okay, so in lower dimension, a chain of one atom per unit cell gets distorted to form a 2-atom cell. Okay, so what happens is, what it is saying, suppose in lower dimensions, let us say one dimension, this particular case, it will have certain dispersion relation, and this thing is your A is this, okay, and it will have certain energy, okay. This is pi by A, and this is minus pi by A. Okay, so usually what happens, so there is this theorem called Pierre's distortion theorem. What it says is that this this particular configuration is unstable, and what is more energetically favorable is if this come together, then what will happen? So this will come together, these two will come together, these two will come together. So what you have is a dimer kind of chain. Okay, and it is proved that this is more stable than this one. So that is why energetically, uh, at energetically from this configuration to this configuration it will try to jump. Okay, that is why this will get distorted to form this two atom unit cell. Okay, now you see that this will have a periodicity of 2a. Okay, and its Brillouin zone will have so its Brillouin zone will be now pi by 2a. Its Brillouin zone will be pi by 2a after distortion. Because now 2a is the lattice spacing. Okay, so basically what will happen is, so what happens is, so there will be a break in this. So there will be a break in this periodicity, and it will try to. So here the energy will try to lower, and here the energy will split. So that will happen because of this dimerization. Okay, and since some of the energy gets lowered, it will be more energetically favorable. So it will be something like this and something like this. Okay, this is the result of the Peirce distortion. Uh, so this statement is true. The electron-phonon coupling is responsible for above dispersion. Okay, what is phonon? Phonon is just, it is a quantum of the vibration of the vibration of this lattice points. So when it will vibrate, it can come together and go further. So it is the electron-phonon coupling which is responsible for the, and so this statement is true. So this is the electronic band state, band gap, electronic band diagram. So we are calculating the energy of the electron, and it is responsible because this phonon mode is there. So because of this phonon modes, it will vibrate. The final energy depends whether the atoms moves left or right. So this actually doesn't depend. So this statement is wrong. Why this statement is wrong? Because it doesn't matter if the lattice point is moving this way, or this way. The energetics remains the same. And it is extremely difficult to form a regular crystalline lattice in one dimension. So this is true because lower the dimension, this instability increases. So these three are the true statements, and this is the wrong statement. So which of the following is true in a low dimension system? So let us look at each of the statements. Electronic structure of nanostructures is independent of size. So this is not true. Why? Because we can try to understand this from a very simple one-dimensional case. So if we have a electron in one-dimensional box of length L, let's say, we know that energy is given by h bar square y square n square over 2 m L square. Okay, here the first thing that comes into play is this L. Okay, and L is size of the any nanostructure. In that nanostructure there will be some electrons. So the electronic structure is not independent of the size of the electron. It actually depends on the size. So this statement is wrong. The surface to volume ratio increases as we decrease the size. So surface to volume, consider the case of a sphere, let's say. Okay. So for any particle, so this statement is true. So we can consider with respect to a sphere, let's say it is surface is 4 pi r square divided by 4 by 3 pi r cube. So this goes as 1 by r. So the surface to volume ratio, let us decrease the size. Decrease the size means R will reduce. If R will reduce, so if R will reduce, S by V will increase. Okay, so this has to increase actually. So this statement is wrong. Similarly, you can prove it for, you can look for any particle. For cuboidal cubic particle also, it is 6 a square is the surface and volume is, let's say it is, so S by V is this, which is 1 by A. So for any particle, the area goes as A square with some proportionality constant, and the volume goes as A cube, some feature size A cube, and it goes as 1 by A. So this statement is wrong. The energy spectrum becomes discrete rather than continuous. So, uh, so let us look first at the fourth statement. The Schrodinger equation is no longer valid at extremely small scale. So this statement is wrong. Schrodinger equation is valid even very small case, even for single particle case. Uh, so it is valid at. So this statement is wrong. Schrodinger equation is valid. So now let us look at the energy spectrum. What happens? So as we go to the lower structure, so as we go to some low dimension, then what happens is the energy spectrum, it will become more and more discrete. Why? Because let us say let us say in 3D. In 3D, what we have is so here kx, ky, kz. Here we will have all these discrete points, and we assumed that the gap between these two is 2 pi over Lx, and gap between this ky points is 2 pi over Ly, and the gap between this is 2 pi over Lz. So now imagine the case where we reduce the dimension from 3D to, let's say we want to go to 2D. Then what would happen? So I'll just so we'll discuss this in the next slide. So in 3D, what we have is kx, ky, and kz. So in 3 dimension, we have this k space, the k states, and we are saying that the gap is 2 pi over Lx. Here the gap will be 2 pi over Ly, and here it will be 2 pi over Lz. Okay, now this Lx, Ly, Lz, these are of the order of centimeter or mm. Okay, so these are quite big. But if we want to go to, what the question is asking? It is asking that for a low dimensional system. So let us say from 3D to we want to go to 2D or 1D. So let us go to 2D first. So from 3D to 1D, if we want to go, so what we want to do is we will reduce one of the size. Let's say Lz is, let's say 1 centimeter initially. So we had this cubic volume of Lz, Lx, Ly. So 1 cm, 1 cm, 1 cm. Now we want to make a 2D material. For the 2D material, what we'll do, we'll take Lz to, let's say, 10 nanometer. So the point is, it is very small, and it is now a 2-dimensional system. So this is really very, very small. Lz is, so now what will happen? The earlier we could think of it as a very continuous, so dkx, dky, dkz, we could think of it as very continuous material, continuous spacing. Now what will happen? This LZ will LZ goes to 10 nanometer. So if you imagine 1 centimeter equal to 10 to the power 7 nanometer. So this gap will now increase by a factor of 10 to the power 7. So here it is very closely spaced, and you will have lot of this kx, ky, kx and ky states, kx, ky, and you will have at a very large gap now this 2 pi by Lz. Now you will have the same kx, ky states here. Okay. Earlier it was so close that you could think of it as continuous. So earlier you could think of it as continuous. Now it is separated by a factor of almost 10 to the power 7 of this particular gap. So we have a discretization in the z direction. Okay. So if you go to again one dimension, then so if you try to reduce, so this is the typical case of a quantum well. Okay. If you again further reduce, and this is 2 dimension. If you want to go to further 1 dimension, then what will happen? In 1 dimension you have to make the another size. So Lz and Ly you have to make 0. Okay, and it is some nanorod will form. In that case what will happen? Suppose if you make this Ly to be very discrete, okay, then what you have is you will have something like this. So the energy states become more and more discrete as you lower the dimension. So that is why this is the only true statement. I hope this point is clear. Now let us look at this particular question. So wire is moving at the speed v centimeter per second perpendicular to the magnetic field. So velocity is perpendicular to the magnetic field, and v it is given as 2 Tesla. Velocity we have to find out, and what is and there is a Hall voltage it is given. So suppose there is this rod and it has 10 centimeter length, L equal to 10 centimeter, and magnetic field, let's say it is going into the page and or into the screen, is equal to 2 Tesla, and the velocity is in this direction. Then what will happen? The electron here, it will experience a so force due to the magnetic field, or the Lorentz force, will be E v cross b, or if you want to just calculate the magnitude, it will be E v b, and so this electron will experience a force in this direction. So electrons will get accumulated here, and here you will get some plus charge, and if you connect it to some potential, potentiometer or potentiometer, you will see some readings here. Okay, and this reading will be so this reading will be related to this will be related to the field developed inside it, field developed due to this separation of these charges. So that will be equal to the electric field E times E, or that we call the Hall field, and it will be equal to V times V by D, V by L. L is the length, or this is just nothing but your EMF, electromotive force. Okay, so now what we have to find is the velocity. So the velocity, so electron will cancel this electron, velocity will be V over L V. So now you have all the values. V is 20 millivolt, so 10 to the power minus 3 volt. You have to take care of the units, okay, the volts, and length is 10 centimeter, which is 0.1 meter, and B is 2 Tesla. It is already in SI unit. So since now everything is in SI unit, you will get the result in SI unit. So what you have is meter per second, or which is nothing but 10 centimeter per second. Okay, so this is your answer. Okay, now uh, this question, the dimensionality of the free electron gas, the energy E dependence uh, of the density of states is given by this, where X is the dimensionality. So what is Y? This you have to find. So one of the very direct method is, we know the example of a three-dimensional case. For 3D case, we know that GE is equal to 1 over 2 pi square 2m over h bar square whole 3 by 2 and square root of E. Okay, so we have to write it as this form. So this is what, 1 by 2 pi square 2m over h bar square 3 by 2 e to the power 1 by 2. So this 1 by 2 we have to write as, so it is 3D case, right? So x equal to 3. Okay, so what we can write this as 1 by 2 pi square 2m over h bar square 3 by 2 e to the power 3 by 2 minus 1. Now you see this 3 is nothing but your x here, so GE is directly proportional to e to the power 3 by 2 minus 1. This 3 is your dimensionality, which is x, so e x by 2 minus y. So from here we get y equal to 1. So this is the case in which you get, so here we took a particular case and then we saw it, but we can prove that this is true irrespective of the dimension of the energy. So it is just E d by 2 minus 1. Okay, so I'll just show you how to prove. So I'll just give you a very general proof of that, how it can be done. So the way we have to do it is, so it is just the similar method I told you about how to get the density of states. So number of states in d dimension, okay, d can be 1 2 3 4 5 6, whatever the dimension of the material. So it is L over 2 pi to the power d that you have to do, and you have to multiply 2 for the spin, and then what we have to do is 0 to infinity. If you convert it into the spherical coordinate in d dimension, then it will be the unit surface of the sphere, and k to the power d minus 1 dk. So if you just take some special cases, for example S3 is equal to 4 pi, so n states will be what in 3D. Okay, so this is what surface area of unit sphere in 3 dimension. Surface area of unit sphere in 3D. It is 4 pi r square. R is 1, so it will be 4 pi. So n states by n states in 3D will be equal to 2L over 2 pi whole cube 0 to infinity 4 pi k, so 3 minus 1 is square dk. Okay, similarly for any other arbitrary dimension that you can do. Okay, so this is the surface area of unit sphere, which is basically just a number. Now what we can do is, so L to the power d, I will write a number of states over L to the power d. L to the power d, I will just write it as volume to the power d. So volume d, okay, volume in d dimension to the power d, so 0 to infinity. So Sd is a constant, so I took it out, so it is k to the power d minus 1 dk. Now we have to use E equal to h bar square k square over 2m. This implies k equal to 2ma over h bar square. So this is just the constant. So k is 1 by 2, a is so okay, k is given by this, and dk will be given by 2m over h bar square, again 1 by 2, 1 by 2 root e d. So we just have to put everything in here. So these are just some constants. Number of states in v is equal to 2 2 root t 0 to infinity. This k, we have to replace this value, 2m over h bar square into e to the over 1 by 2 to d minus 1. Okay, and it is dk is 2m over h bar square d e by 2 root e. So this thing is proportional. So number of states per unit volume is nothing but g of e dE. Okay, g of d in d dimension. So I will just write the subscript d is equal to is equal to this quantity. Now what we have is, we can take g of e is directly proportional to whatever is the coefficient of this dE, whatever is before dE. So it is e to the power 1 by 2. So from here what we get, e to the power 1 by 2 d minus 1, and e to the power so e to the power in denominator it is 1 by 2, so it is minus 1 by 2. So this is e to the power d by 2 minus 1 by 2 minus 1 by 2, which is nothing but e to the power d by 2 minus 1. So the density of states in any dimension is of this form. Okay, so is of this form as long as e is equal to h bar square k square. So here it is the very important input. So as long as the dispersion relation is this, so for this dispersion relation, e is equal to h bar square k square by 2m, this statement is valid. Okay, so this is how you have to do it. Okay, now we go to the next question. Choose the choose the incorrect statement from the following. The first statement, let us see, the reactivity increase with decrease in particle size. If the particle size decrease, then surface to volume ratio will increase, and if surface to volume ratio will increase, then there will be more surface area for reaction to happen, area for reaction to occur. So reactivity will increase. This statement is true. The surface to volume ratio increases with reducing size. This we saw just in the previous question. So this is also true. In semiconductor, the band gap will increase as the cluster size is decreased. So this statement is false. So as just like we saw the case of a particle in a box problem, as you reduce the dimension, energy will start increasing. So similarly will be the case of this band gap. So band gap will start increasing as the cluster size is decreased. As we decrease the, so this is a wrong statement. As you decrease the size of the particle, the continuous density state in the band is replaced by set of discrete energy levels. So this also we discussed in in just a previous problem. So when we had a very continuous one, uh, and as we decrease the size, it became very discrete, the energy levels. So this statement is true. Which of the following represent correct expression of velocity dispersion relation and effective mass? So, so this is just a general question. We discussed in the previous question that the velocity is given by 1 by h bar and the gradient of the energy, where energy is a function of the wave vector. So this is your energy dispersion relation, and the effective mass, it is given by h bar square over the second derivative of the energy dispersion relation. This also we discussed in some of the previous question, and only this answer matches, so this is the answer. So with that we have discussed all the questions of assignment 5 of the previous year and assignment 4 of this year. If you have any doubt or questions, you can ask. This is fine, right? If do you have any questions or doubt?
Hello, Share.
Yeah.
The discussion videos only week 1 and week 2 are uploaded, perhaps. The
No,
other discussion videos are
I think
problem
all are
solving discussion videos.
there. I think all are uploaded now. You can just uh, so all the videos are uploaded. This will be also uploaded. Okay, so you can go and follow.
Uh,
Okay.
I had actually checked in that there were only two videos, week 1 and week 2.
Okay, or you can just go to this and you will see the. Good evening, everyone. Today, my name. Okay, you can go to the channel and you can just find uh, you can find the playlist over there. Okay, so there will be a
Okay,
playlist, electronic theory of solids. You can always go
okay.
and find there. Fine.
Where it is in the YouTube?
Yeah, in YouTube it is there, and it is public, so you can access anytime.
Okay, okay, okay. All right, sir. Thank you. So I can we can find out the all the videos till date, whatever
Yeah,
the
yeah, you can
discussion videos
find
are there.
so up to now this video it will be also uploaded today, so you can find all the videos there, or you can follow uh, this link
Okay,
also, the one which I showed you just before.
okay,
There was this video, that also you can follow.
okay, okay. Here it is actually there three videos are there.
Yeah, yeah. Okay,
Lives.
this will be uploaded as soon as the session is ended.
There are three, but for today there are the I think it is the fifth week discussion week.
uh, no, I guess it is the fourth one.
One, two, three, four. Fourth one. Okay, okay. Yes.
Yeah,
Okay, okay. Okay. Two we are there actually. So another the third week and fourth week videos will be there.
yeah, this is the fourth week video, the current
Ah,
one.
yes. Uh-huh.
Yeah. Do you find the sessions useful and you are able to solve assignment?
Ah, yes, yes, yes.
Okay. If you have any question or doubt, you can ask like during the. You can stop me in between and you can ask the questions. Okay.
Yes,
I
yes,
hope you are
yes.
understanding whatever I'm saying in the session, how to solve the problems.
Yes. Thank you.
Okay.
Good night, sir.
Okay. Thank you so much. I'll end the session.
Thank you.